Major and great earthquakes are usually followed by hundreds or even thousands of smaller earthquakes, called aftershocks, that occur along and adjacent to the fault displaced during the large earthquake. In some earthquake sequences, a smaller earthquake, called a foreshock, precedes the main shock, like the one that occurred 2 days before the 2011 Tohoku-oki magnitude 9.1 earthquake. With rare exceptions, all magnitude 7 to magnitude 9 earthquakes have a collection of smaller magnitude aftershocks that can occur for weeks, years, or even centuries after the main shock. On the other hand, many major and great earthquakes do not have a foreshock preceding the main shock. Important observations about foreshocks and aftershocks are provided by the 2002 magnitude 7.9 earthquake in the Alaska Range. First, some background. The Alaska Range is a narrow, 650-kilometer-long mountain range far from the subduction zone plate boundary. The Yakutat terrain was an oceanic plateau that traveled northwest on the Pacific Plate and began colliding with the continental margin about 25 million years ago. It now acts like a geologic snowplow, driving immense blocks of continental crust in a counterclockwise rotation. Right lateral strike-slip faulting along the Castle Mountain and Denali faults accommodate this crustal block rotation. At a magnitude 7.9, the November 3, 2002 Denali main shock was one of the largest strike-slip earthquakes in North America. The earthquake rupture started at a depth of 5 kilometers, with 4 meters of displacement on the previously unknown Susitna Glacier Fault. It continued with up to 8 meters of right lateral displacement on the Denali Fault, and then branched onto the Tachunda Fault for a total rupture length of 340 kilometers. Let's now examine the entire sequence of earthquakes that occurred along the Denali Fault from late 2002 into 2003. The sequence started on October 23rd with the magnitude 6.7 Nenana Mountain earthquake that was followed by aftershocks spread over a 45-kilometer-long segment of the Denali Fault. The resulting fault displacement decreased shear stress on that part of the fault, but increased stress on the adjacent segment to the east. On November 3rd, the magnitude 7.9 main shock occurred, with the epicenter located 22 kilometers east of the magnitude 6.7 epicenter. The October 23rd earthquake is now called a foreshock because it triggered the magnitude 7.9 main shock 11 days later. However, we didn't know it was a foreshock until November 3rd, when the larger main shock occurred. That magnitude 7.9 main shock was destined to eventually occur, but was hastened by the change in stress caused by the foreshock. Seismologists have analyzed countless foreshock main shock pairs of earthquakes, and earthquake triggering in general. Unfortunately for earthquake prediction, there are no special characteristics of an earthquake that let us know it is a foreshock of a larger main shock that is yet to come. The major redistribution of stress during the main shock triggered an aftershock sequence of smaller earthquakes along the main shock rupture zone. Aftershocks are smaller earthquakes on patches of the rupture zone and adjacent smaller faults that occur as rocks along the rupture adjust to the new state of stress. 760 aftershocks of magnitude 3 or larger occurred during the 30 days following the November 3rd main shock. The entire earthquake sequence reduced a large amount of shear stress that had built on the Denali Fault over the preceding decades and centuries. 14 aftershocks had magnitudes greater than 5, and the largest occurred 10 minutes after the main shock with a magnitude of 5.6. In general, larger aftershocks are concentrated in the hours to days following the main shock. Remember, the magnitude scale is logarithmic, and elastic energy released by an earthquake increases by a factor of 33 with every unit increase in magnitude. So, at a magnitude 5.6, the largest aftershock released less than 1/1000th of the energy released by the magnitude 7.9 main shock. On this graph, we can see that the rate of aftershocks dies off with time after the main shock. This rapid decay in the rate of aftershocks was first studied in detail by Fusakichi Omori, one of the most important figures in the history of seismology. Omori examined aftershocks of the magnitude 8 Nobi earthquake that occurred in central Japan in 1891. The Nobi earthquake is the largest instrumentally recorded inland earthquake in Japanese history. Omori found that the decay of the aftershock rate was best analyzed using a logarithmic graph of aftershocks per day versus days after the main shock. He showed that the rate of no-B aftershocks decreased with the reciprocal of time since the main shock. This is a general observation now referred to as Omori's law. Plotting data for the 2002 Denali earthquake sequence on a logarithmic graph shows that the decay in the aftershock rate follows Omori's law. In a typical main shock aftershock sequence, 97% of the energy is released by the main shock, while the hundreds to thousands of aftershocks release the remaining 3%. Although only a portion of the energy of an earthquake sequence is released by the aftershocks, the largest aftershocks and the highest rate of aftershocks occur during the critical first hours and days immediately following the major earthquake. This is exactly the time when emergency workers are locating and rescuing injured people from collapsed or damaged buildings. Because those buildings can shift or even collapse during aftershocks, rescuers are at greatest risk when their expertise and service is most important.